Welcome everyone. In this video we will take a look at an AP Physics C Mechanics exam question. Now the question comes from the 2018 exam paper, and I will attach the original exam paper and the official solution by the College Board to the descriptions part of this video so that you can take a look at the original documents yourself. So let me give the question number as well. This is 2018 AP Physics C Mechanics, and this is question 3 from the free response booklet. So for the A part of this question, we are given a rod in that looks like a triangle. It is with a length of L. We're told that this is x equals 0, this is x equals L, alright? And we're given the density, the linear density, mass density function lambda. This is defined, this is given to be 2m over L squared times x. M here is the total mass of the triangular rod, and x is the distance from one end of the rod, from the left end. Now for the first part, we are asked to use integral calculus to show that the rotational inertia of the rod about its left end is ml squared over 2. So for A, we're asked to show that, let's say, the moment of inertia with respect to the left end, so L I will call it, we're asked to show that this is 1 over 2 ml squared. And also, you might have noticed that I am already explaining the question and giving what the question states. But if you want to have a look at the paper while you're watching the video, you can just click on it from the descriptions part, have it open on another tab, look at the question, and then try it on your own maybe, and then watch the video to see the solution, okay? So we have this. And then, well, how do we show this? We will use calculus as the question suggests. So, we start with the definition of moment of inertia. And remember, we're finding the moment of inertia with respect to the left end of this rod. This will be the integral sum. We will have dm, we will have a small mass. Let's say we chose it here. This is the dm. It will have a width dx. And it will be also at a distance x to the pivot, to the origin that we choose. And we will multiply it by x squared because this is the definition. Now, how do we take this integral? As x squared varies, dm varies, so we need to really get dm in terms of dx so that we can take the integral. Alright, and it is quite easy actually if we notice that the lambda is actually another way to say dm by dx. So this means that dm, the infinitesimal mass, is equal to, well, let's see, it is going to be 2m L squared x dx, right? I just use this equality. I'm then going to substitute this right here. And when I do that, we will have the integral 2m L squared. We had then x here and x squared in the original integral, so that gives you an x cubed. You have the dx. Now the good part is we can choose the boundaries, and we know that x runs from 0 all the way to the whole length, so L. Well, how do we take this integral? 2m divided by L squared, that's a constant. What is the integral of x squared dx? That is x to the 4th divided by 4. So you have 2m x to the 4th divided by 4L squared. And you have the boundaries L and 0. When you evaluate the antiderivative at the boundaries, you will see that you get 1 over 2m L to the 4th divided by L squared minus 0. So that is 1 over 2m L squared. And that is the requirement of the question. So the first part, that's done. And that was 3 points, by the way, if you wonder. Okay, so moving on with the B part of the question. B part. we are given a system. We are given a hoop like this. We're told that the mass of this hoop is capital M, the radius of this hoop is L, and we're even told that the moment of inertia, the rotational inertia through its center, so maybe we call it C, IC, is ml squared. We are given this. Now to this system we add three rods, and these rods are the rods that we have. These three are identical rods to the one that we just computed in part A. Okay, so they have length m, they have length L, they have mass m, and their density function is this. So what are we asked to do in this one? We're asked to derive an expression for the rotational inertia of the hoop rod system about the center of the hoop. We will express our answers in terms of m and L and any physical constants. So how do we start? Well, we will say that the total moment of inertia will be, since the moment of inertia is a scalar, we will just add the moment of inertia of different parts. We will have the moment of inertia of the hoop, plus we will have the moment of inertia of the three rods. So three, and then we have the rod. What is the moment of inertia of the hoop? That was given by the question. It is ml squared, plus we found the moment of inertia of the rod to be 1 over 2 ml squared. So we have 3 over 2 ml squared. That is just 5 over 2 ml squared. And I remind you that this is through the center of the hoop. Alright. And this was, let's see, this was 2 points. Check. For part C now. For part C. In part C, we're told that the hoop rod system is initially at rest and held in place, but is free to rotate around its center. A constant force F is exerted tangent to the hoop for a time delta t. So we have some force which is constant, and we have a time interval delta t. We're asked to derive an expression for the final angular speed omega of the hoop rod system. Express your answer in terms of m, L, F, and delta t, and possibly any physical constant as appropriate. So how do we tackle this problem? Well, there are different ways, but the way I want to solve it is using the fact that the time derivative of angular momentum is the torque. Since we have a constant force, we can translate this formula to say that delta L, the change in angular momentum, is equal to torque times delta T, the change in time. What is delta L? Well, it is going to be delta I, the moment of inertia of the system, times omega. And for the torque, we will have, well, it will be force times the moment arm. The force is F. What about the moment arm? We are told that it is tangent to the hoop, so the moment arm is the radius of the hoop, which is given to be L, and then we have delta T. Now, on the left part, we know that the moment of inertia of the system won't change when a force acts on it, so we can take it out of the delta. We have then I delta omega equaling FL delta L. Oh, this is delta T, right? Change in time, excuse me. We have that, and we know that this motion starts from rest, so delta omega will simply give us omega, which then means that I will say delta omega equals omega, so this is going to be FL delta T over the moment of inertia, which we found to be 5 over 2 ml squared. So when we simplify, 1L cancels, we have 2F delta T over 5 ml as the final answer to part C. And if you wonder, this part was worth 3 points. Great. Now moving on with part D, we are told that this hoop rod system is on an incline. Let me draw it with my perfect drawing skills. I'm just kidding, of course. You can see that I draw very bad. Though I would like to learn how to draw. That is, I think would be good. Now we have this situation, and we're told to find the free body diagram, to draw the free body diagram of the hoop mass system, or hoop rod system, I mean. So we have this dashed line which represents the incline. We have the hoop. Let me draw the rods as well. Cool. And then, well, we will of course have the force of gravity downwards from the center of mass of the whole system. Now this force wouldn't equal mg. It would equal 4 mg. Why? Well, because 1 mg here, 1 mg here, 1 mg here, and remember, the hoop also has a mass of m, so 4 m's gives you 4m. And then we will have the normal force from the surface to the hoop, and it will be perpendicular to the surface. It will go through the center here, okay? It will be in the radial direction. If it is perpendicular to the circle, it means that it passes through the center. And then we will have the force of friction. Now, how do we find the direction of the force of friction? Obviously, it will be up the incline or down the incline. But the key idea here is well, maybe I should have said this, but the rod is moving like this. So, and it is moving without slipping. So the omega is like this. And in that case, the force of friction will oppose the direction of rotation, because it is against the tendency of motion, right? And a point here would be tending to go this direction. I know that at the contact point between the surface and the hoop, there is so the velocity there is 0 because there is no slipping. But just to the right of the point would be trying to go to the left. So the tendency of motion is down the incline. That's why the opposing force, the friction force, should be up the incline. Okay, that's the force of friction. And this was worth 3 points. We checked this question as well. And for the I part, 2I part of D, we're asked to give reasons for our choice of direction for the forces. Well, we discussed F, it should oppose the tendency of motion. It is in the opposite direction of the rotation. And the normal force will be perpendicular to the surface. It goes through the center of the hoop system. And the force of gravity is downwards, of course. Alright, those are our explanations. And that part was worth a point. Cool. Now, last but not least, we have E. E says, and I quote, derive an expression for the change in height of the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches its maximum height. Express your answer in terms of M, L, I total, omega, and physical constants as appropriate. Okay, so we are allowed to use M, L, I total, the total moment of inertia of the system, omega, and possible physical constants. So how do we tackle this? Well, we say that the energy will be constant because there is no slipping. The work done by the friction won't be negative, it will be 0. And so what is the maybe if I choose this as the 0 line, if this is the initial height where we start, well, it should be at the bottom of the ramp though, right? So let me erase it. So let me draw it here. We start at the bottom of the ramp like this. I choose it as 0 height. So let me even adjust the incline to my preference. Okay. So it starts there and it will be here at some point. I call delta H. Now, all of the kinetic energy, initially we only have kinetic energy. All of it will be transferred into potential energy. Now, for the kinetic energy though, we need to be very careful because we don't have just rotation or just translation. We have both. So we will say that the initial energy is 1 over 2 I omega squared. And this will equal the energy at the top point. The kinetic energy is 0. The hoop rod system comes to a rest. We need to find the potential energy, gravitational potential energy, which is G delta H multiplied by the total mass, which is, remember, 4m. Not m, but 4m. And I want to mention here that this I is not I total. Because if we're going to use this short way of calculating the kinetic energy, we need to choose this I to be the moment of inertia that goes through the instantaneous rotation point. I don't know, what was it called? So it is called the instantaneous axis of rotation. It is the point where the rod, why do I say rod? It is the point where the hoop touches the surface. It is this point. So what is the moment of inertia with respect to that point? It is going to be the moment of inertia through the center. I'm using the parallel axis theorem. So it will be through the center, which is I total, that is by definition, plus by the parallel axis theorem, it is the total mass multiplied by the distance between the vertical distance between the two axes squared, so it is L squared. Then we will have, well, that's it actually. We will solve for delta H. It is going to turn out to be I omega squared over 8mg, and we just found I. It is I total plus 4ml squared. Oops, excuse me, ml squared. Omega squared all over 8mg. And that is the final answer to the question, which was worth 3 points. So this is it. I hope that this video shows you how an AP question can be answered, how do we approach it, and I hope that it helped you to understand a physical concept better. Also, this is a disclaimer. I'm not saying that the work that I have shown here would get full credit on the AP exam, right? It may be not get full credit. They may say, hey, you didn't show enough work, hey, you didn't do this, you didn't do that. So I'm not claiming that, but you can trust me that the answers are correct. Also, why do you even trust me? Just look at the descriptions part and you can see the official solutions to yourself, and you will see that the results match. But as I said, the exam graders could consider some parts to be not fully explained perhaps. So I'm not saying that you should take this video as an exam suggestion, but rather take it as a physics suggestion, as a way that you approach problems, not exams, okay? Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.